Hello, everyone. Okay, thank you for attending our presentation session. So I think we can get started. Okay. So hello, everyone. This is Jingjing Sun from Meta Power Team. So today, together with me is Bo-Wen, also power engineer from Meta, and Mohammed is our mechanical engineer. So we will give a presentation on the high power rack V3. Basically, it is a 50-volt set power rack. We will briefly introduce the designs. Before we started, also, I would like to thank Dimitri, another mechanical engineer who has contributed a lot to the overall HPRV3 mechanical design and to these slides. Okay, let's start. So this is our agenda. So we will first go through the overview design of the high power rack, HPRV3 set power rack, from the concept to the key components and then to the application cases. Then we will talk more details about the mechanical design of the overall HPRV3 architecture. And lastly, we will give a detailed example of a specific power system, including the operations and implementation. So in this page, you can see on the right side, this is the overview of the side power rack, where you can see we have one IT rack, and a side of it is a HPR side power rack. So in between, we have horizontal bus bars on the top area and bottom area to connect these two. So why we need such set power rack architecture? Basically, it's driven by the rapidly increased power demand from the AI workload. We know that for the single IT rack, currently there's no sufficient space to accommodate all the IT gear equipment and also the hardware hardwares. So with the dedicated set power rack, we can create more space for those to stepping up more power hardwares. And also in this design, we don't have extra power conversion stage. And also we based on the traditional 50-volt DC bus distribution system. So overall, we still maintain the high end-to-end power delivery efficiency. And also we create space. We can maintain less system design changes and implementation complexity. So currently in Meta's design, the power roofline we have for this set power rack is up to 300 kilowatts DC power, but in the real application, given the pulse loading impact from the GPU load, we do need to consider power deratings. So it's up to around 250 kilowatt per rack. So these slides, we will talk more details on the key hardware components inside the side power rack. Still here, we present the front view and rear view of these side rack, dual rack systems. So the rack is still based on the standard HPR rack with minor modifications. And for the power shelf-wise, currently we can deploy 2 generations of the high power power shelf system. One is the 33 kilowatt PSU and the BBU power shelves, and second one, which is still in development, but we are targeted to have the mass production early next year, which is the HPRV2. So each power shelf is around 72 kilowatt output power for both PSU and the BBU. And for the bus bars in such dual rack power system, we have 2 types of bus bar. One is the vertical bus bar on both the IT rack and the set power rack. Second one is the horizontal bus bar, bridging these 2 racks. So for horizontal bus bars, currently we have 2 versions. One is purely the passive version. Second one is we have internal fans to help improve the thermal performance and the overall power rating. So for the vertical bus bar, we also have 2 versions. One is the air cooled version. Currently is used for the, inside the side power rack. The second one, we also have a liquid cooled version, which can boost up the power rating up to 700 kilowatts. Currently, we already used it inside the IT rack. So we also have an optional power device, which is the supercapacitor trails. This one is used for the case where we have the pulse loadings from the GPU load. So it can help buffer the pulse load and smooth out the input current. And for the communication-wise, we still use the WED400 based on the Modbus communication. So currently for in Meta, we have several different platforms that is planned or deployed with such side power rack. One example is the GB300 rack based on NVIDIA's GPU. And we already ramped up this rack. You can see the overall structure of this rack. And in parallel, we are trying to boost up the power roof lines of the side power rack. So this includes, we will also deploy and use the liquid-cooled vertical bus bar to improve the overall power roof line of the side power rack. And also, we will soon to implement the 72 kilowatts output power shelves. And this also includes, we will add more slots to add more horizontal bus bars and with better cooling performance of the bus bars. So next, I will hand it to our mechanical engineer to introduce more details on the mechanical design. Yeah.
Yep, thanks, Jingjing. So getting into the mechanical design of this new side power rack architecture, we had to make some changes to some existing hardware and then introduce some new hardware as well. So main changes are to the vertical bus bar. Here we have kind of an overview slide showing the changes that we made. The first one being specifically on the power rack vertical bus bar, we have a physical split halfway up the vertical bus bar, so between OU 22 and 23. And what this does is it splits the power rack vertical bus bar into an upper and lower power zone. And the purpose of doing that is to enable better current sharing between the horizontal bus bars. We also had to make changes to the front and back of the vertical bus bar at specific OU locations. So the first item there is at OU 3 through 8 and 37 through 42, we had to make changes to the front side in order to enable our new 72 kilowatt power shelf bolted bus bar connections. And then from OU 1 through 6 and 39 through 44 is where we have our horizontal bus bar connections, and those require some modifications at the rear of the vertical bus bar, and I'll get into those details in the next few slides. Going into more detail on those front side changes, so once again, we have a bolted connection on the vertical bus bar for our next generation power shelves. Once again, this is at specific OU locations, so we had to core out some copper to allow for this new bulkier bolted connection. And of course, we had to add some threaded hardware into the bus bar as well. Into that next picture, we have this new modular grounding bracket with removable 1OU ground blocks. I'll get into that in a little bit more detail in the next slide. And then finally, we have some removable toolless covers. These are to allow for safety, to ensure that you don't have exposed copper, as well as ease of serviceability in case you need to go in there and service a bolted connection. So getting into why we even needed to do this in the first place, at least for the front side changes for the power shelf. Our next generation power shelves are high power density, and at the time of development, there was no bar clip connector that could handle the current carrying capacity that we needed. So once again, this is done at specific OU locations. I do want to stress that while you can only install the power shelf in these OU locations, it doesn't mean that you can only install a power shelf in those locations. You can continue to install your regular IT gear, and that's the whole purpose of that modular grounding bracket that I had talked about earlier. Getting into the rear side, so these changes are to enable the horizontal bus bar connections. So once again, we have to core out some copper, not nearly as much as the front side for the bolted connections, In this case, we're just enabling a traditional bar clip connector to be installed here. So pretty similar interface to what you would see on the front side of an existing HPRV3 or HPR vertical bus bar. And then additionally, we've added these alignment brackets. These have features for alignment of the horizontal bus bar, as well as features for the horizontal bus bar to latch into the vertical bus bar. Getting into alignment, so when you have a 2-rack system, power rack and an IT rack with a semi-rigid member going across them in the horizontal bus bar, you want to make sure that they're actually aligned properly, and you have a process to do that repeatedly. So in the Z direction, we continue to use the leveling feet. This doesn't change. And then in X and Y, we've introduced this new alignment bracket. It'll be at the top and bottom. And this allows you to actually align the racks in the X and Y direction and eventually allow you to install that horizontal bus bar. So I think I talked about this in the previous slide, but yeah, those leveling feet can be used to align the rack in Z, and then the alignment brackets in X and Y. I'll get into the actual horizontal bus bar design overview here. I won't spend too much time on the actual details here. There's a presentation later today with some of our colleagues that'll go into this into a bit more detail. But essentially, you have an enclosure, and then you have a positive and negative bus bar going across. You have a bar clip connector at either end, some alignment pins, some latching features, and then you have a flexible section in the middle. The purpose of that flexible section is to allow for you to eat up any tolerances that may occur during that rack-to-rack alignment. And then getting into how all of this gets put together. So those alignment pins on the horizontal bus bar engage with those features on this new alignment bracket. And then the latches engage with those same features on the alignment bracket, and you can just install the horizontal bus bar in the Y direction. And with that, concludes the mechanical design section, so I'll hand it back over to Bo from the power side.
Thank you, Mo. So I'll give an example using the Sedge rack. This is the example we are working on with our partner. So the ITGR are hosted in the ORW rack. You already heard a lot about that. All the power components and power rack management devices are located in the Sedge rack. So this one has 12 kilowatts PSU unit inside it, and each shelf has 6, so 72 kilowatts per shelf. We have 6 of them in the power rack. It was located top and down because the power rack is, has 2 power zones. For BBUs, we have put 4 of them. Each one is, BBU shelf is 72 kilowatts. We also have 12 supercapacitor tray located close to PSU and horizontal bus bar. Each of them has 24 kilowatts. The horizontal bus bar is a fan-cooled horizontal bus bar. Connect the stack card to the RW rack. The power rack has a vertical bus bar. It has split in the middle, so it has 2 power zones. The RW has a liquid-cooled bus bar hosting the ITGR. The rack management device is Wedge 400. It serves as coordination of the power devices and also doing monitoring of the power rack. So this page shows the details how the whole system works. So we have Wedge 400 managing all the power devices. We split them into 4 Modbus ports. So port 1 is managing all the PSU and the BBUs, and port 2 manage 8 supercapacitors, and port 3 manage 4. Current sharing between each kind of devices. So PSU 6 shelves, they have power sharing information shared so that they can share the load. Also for BBU and the CBU, but we connect the PSU share information to the CPU shelf so that CPU knows how to help PSU to smooth out the GPU load. PSU shelf also send the AC power loss signal to both CPU shelf and the BBU shelf. Once the AC is lost, supercapacitor tree will stop working and the BBU will start powering the IT rack. CPU and BBU shelf also has synchronization between all shelves so that they can work all together. So that is a small example, and back to Jingjing for the last slide.
Okay, thank you, Bo. So I think that's all the main contents for our presentation. So lastly, we would like to call to actions. So there is a QR code. So feel free to scan it and provide any of your feedback, including comments, questions, and also any suggestions. We also have another a presentation which is delivered by Dimitri. We'll focus more on more details on the side power rack, especially on the mechanical design. Okay. That's it. Thank you, everyone, and welcome any questions.